my name is Mariella Rivas, and I have a background in actuarial science at the BSc level. After that, I would have completed the MSc Statistics degree, both at UE. And from there, I would have went on to pick up an internship in data science at TSCT. After which I would have accepted a permanent offer with Guardian Group, and that is where I've been for the last year and a couple months in data science as well. My passion really includes machine learning, big data analytics, visualization, and yeah, I really hope that you all would enjoy my presentation tonight. I will be sharing on a paper that was recently presented at the 2022 International Conference on Advanced Communication Technology. This is an IEEE conference, and our paper was entitled Premium Rate Services Fraud Detection. And in it, we would have focused on proposing a suitable machine learning solution to fraud detection in the telecom industry. In particular, we would have compared a traditional accuracy-based modeling approach to its cost-sensitive counterpart in order to highlight the advantage of a cost-sensitive model in this scenario. We will begin by explaining what motivated this research, and then we will move on to highlight some of the existing works on this matter. After that, we will examine our approach to providing a solution for this problem, and then wrap up with our conclusions and recommendations for future research. So basically, premium rate services fraud, or PRS fraud as it's abbreviated, this happens when fraudulent calls are generated from a telecom network to high-cost destinations. And this activity usually results in leaked revenue, which is only worsened by the difficulties companies face in profiling a fraud case, or even identifying these cases before they actually occur, especially for smaller countries that may still be developing. And so we examined the use case of a telecom company in a small developing state to conduct our research, and provided a model that would allow timely detection and termination of suspicious calls with the intent of reducing the revenue leakage caused by these events. On this slide, we can get a closer look on how premium rate fraud occurs. There are two common methods. Firstly, on the left, a premium rate number owner can advertise to generate calls to his number. A well-known example may be psychic lines. And when a caller takes the speed, the call is routed through their service provider, who pays the premium rate number provider an extra fee. And this revenue is what is shared with the owner of the premium rate number. Another way in which PRS fraud is conducted would be through PBX boxes that are compromised. This is where telecom companies' PBX equipment can be hacked for illegitimate calls to be placed unknowing to the company to high-cost destinations. And of course, the company must pay its carriers for these calls, and more often than not, the hacker has a deal with these carriers and would receive part of the revenue that is generated by their illegal activities. Now, a reasonable amount of research has been previously conducted, exploring various solutions for timely detection of such fraudulent calls. And machine learning has been at the center of these studies. For example, in our research, we would have found these two papers here that, their ML solutions performed remarkably well. For example, in 2015, there was a Cortex-Square support vector machine that was developed, and they used callers' historical usage data, and their model achieved over 90% accuracy in detecting PRS fraud cases in a timely manner. Then in 2018, another paper also used historical call data to explore various machine learning solutions to this problem. And the most effective model came out being the support vector machine in this case as well. And it allowed a 90% decrease in illegitimate calls for that use case. In our study, however, we would have taken things further to factor cost sensitivity into our selected model. And this is something that was not found to be previously well explored in the telecom industry for fraud detection problems. But we would have looked at the success of such an approach in the medical industry, as was illustrated in these two papers. One in 2007 that used a cost-sensitive decision tree approach to medical diagnosis, and another one in 2020 that explored a similar approach with benefit optimization to classification problems for medical data. And leveraging the approach that would have been taken in these two papers, we adapted a similar stance in our research. So taking these two related works into consideration, we can now look at our solution. For our use case of a small developing country, we would have structured our solution as we have outlined here. We would have used variable information gain and pairwise feature correlation to conduct a feature selection exercise, validating the results with Ward's hierarchical divisive clustering. After that data cleansing phase, we would have built our traditional accuracy-based classification tree and its cost-sensitive counterpart. And then we would have compared the performance of both models in terms of predictive accuracy and cost savings. Here we have some of the key features that were selected in the pop-out box to the right. Like I said, information gain and correlation were used for determining the best features for modeling. Information gain basically measures the reduction in entropy by splitting the data set based on given values of a random variable. And it is commonly used in feature selection and construction of decision trees. Variable information gain usually lies between 0 and 1, and we prefer to have a higher value, as this would minimize the entropy and aid in effective classification. And so if any feature had high correlation to another feature with a higher information gain, and if the first feature itself had a low information gain on its own, it was excluded. And so there were initially 23 variables, but this way we would have omitted 5 of them and remained with 18 being selected for use in our model. Some of the main ones, they're listed here in white. Call date, day, and time, they were crucial to determining whether a call is fraudulent or not, as well as things like the actual phone numbers, the dialing number, and the dial number. The number of consecutive calls that were made daily, and per dial number, and the call durations and the charges attached to those calls. Once we selected our 18 variables, we ran them through a clustering algorithm. Like I mentioned, we would have used the Ward's hierarchical divisive clustering algorithm, and it was done on a sample of 1,000 calls, just to ensure that the 18 selected variables appropriately classify our data. We see that we obtained a favorably high divisive coefficient. It's 0.97. And also from the plot here, we see that the data points are grouped into 2 distinct categories. And the cluster sizes make sense as well, as we do expect the fraudulent calls to be a minority group as compared to the pool of legitimate calls. In terms of modeling, we opted for a classification and regression decision tree approach, as these models tend to be transparent and they give an explicit representation of the decision-making process. They also tend to be effective for handling both categorical and numerical data. And so we first explored a traditional accuracy-based CAT model, and this model achieved a predictive accuracy of 89.7%, with an AUC of 0.91. This performance was deemed as acceptable, but of course, room remained for improvement. However, if we bear in mind that false positive and false negative errors would translate to actual impacts on the company's revenue levels, we were pushed to go further to construct a cost function that allowed us to apply cost to false negative and false positive errors in our model. A false negative error in this case would represent a scenario where an actual fraudulent call is not flagged by our model, and we let the cost associated with that error be 1. Then we represented the cost of a false positive error as a fraction of that false negative error cost, in this case as 0.1. Of course, the false positive error would represent a case where a legitimate call is flagged as fraud by the model, and this can apply for customer service if a true customer's calls are being terminated. The first thing we noted with this approach is that the predictive accuracy, although it stands acceptably at 84.5%, it did decrease by about 5% when compared to the previous model. However, if we change our perspective a bit from using predictive accuracy as the measure by which we compare our models, and we look at the cost attached to error in both models instead, we can compare the cost-sensitive models cost to that of the accuracy-based model. And we actually see from the line graph on the right here that for increasing levels of error, the cost-sensitive model actually adapts and allows increased cost savings, which is a major advantage that this model provides over its traditional equivalents. All this being said, it was found that both models performed acceptably well, but that the cost-sensitive model can provide the advantage of tangible cost savings. And so it is this model that was posed for implementation, and future research, where future iterations of the model can consider other quality variables or alternative training and testing splits, or even resampling the data for improved performance. Here we have outlined some of the related work that we mentioned earlier as references. I want to thank you all for listening. We have come to the end of my presentation. I hope it was insightful. And at this time, I'm open to your questions.
Yeah, thanks, Mariella. Nice presentation. Just curious, did you do new slides for this talk? Because it looks different to the one for the conference, right? Or is it the same one for conference?
They're a bit different.
Okay, yeah, because it looks a little bit different.